Section 6.5 Semaphores. Semaphore ice is an integer variable. Apart from initialization, semaphores can only be assigned via two atomic operations, wait and signal. So you must know atomic operation, wait, signal, that means can only be operated in kernel mode, because only in kernel mode can satisfy atomic operation. If in user mode cannot, we cannot ensure atomic operation. That means that doesn't be interrupted in the middle of the operation. Okay, so you can see as for the operation with ice, it means this: if ice, the value of ice smaller or equals to 0, then do nothing, just loop again and again. And if ice larger than 0, then ice minus 1, decremented by 1. So from to some point, it means that if we use wait operation, mean we require some resource from operating system, from the system. Okay, for signal operation, it means that just incremented semaphore ice by 1. So we can see if we call signal operation, that means the user have finished using of the results and return to the system. So okay, here I want to emphasize that we just use pseudocode to describe the wait and the signal operation, because we doesn't refer to the discrete operating system. Okay. So atomic operations means one precise modifies the semaphore value. No other precise can simultaneously modify that same semaphore value. So wait, also termed as P operation, and signal as V operation. So we can see, so just now I emphasized, as for atomic operation, can only satisfy in kernel mode. Okay, so the wait or P operation, the signal or V operation can only be implemented by operating system. Okay, so this means the operating system should supply this system calls. Okay, semaphore implementations. The definition of the wait and the signal semaphore operations just described present the same problem. To overcome the need for busy waiting, we can see here, as we define the wait or signal operation, especially wait operation, we have busy waiting. That means if the value of I is smaller than 0 or equals to 0, we just loop and loop again, do nothing. So this is busy waiting. Okay, loop until the time slice expires, then the precise call wait operation will reclaim the CPU to the system. Okay, so this is busy waiting. So we doesn't solve the problem busy waiting. To overcome the need for busy waiting, we can modify the definition of the wait and signal operations as follows. One precise executes the wait operation. One precise execute the wait operation and finds that the semaphore value is not positive, it must wait. That means the precise code wait operation will be put into the waiting queue, okay, will be blocked. However, rather than engaging in busy waiting, the process can block itself. So who can block the process? Only operating system, because this involve the CPU scheduling. Okay, so the block operation engaging. However, rather than engaging in Beijing waiting, the process can block itself. The block operation places the process into a waiting queue associated with the semaphore, and the state of the process is switched to the waiting queue. From running state changed to waiting state. Okay, the control is transferred to the CPU scheduler, which selects another process to execute. A process that is blocked waiting on a semaphore ice should be restarted when some other process executes a signal operation. The process is restarted by a wake-up operation, which changes the process from the waiting state to the writing state. The process is then placed in the writing queue. The CPU may or may not be switched from the running process to the newly ready process, depending on the CPU scheduling algorithm. So if the CPU scheduling algorithm is the priority scheduling algorithm, and if the process that is ready just now, its priority is higher than the priority which is running now, then it is pre-inputted. Okay, so a process that is blocked waiting on a semaphore ice should be to implement semaphores under this definition just we talked, we define a semaphore as follows. Okay, here define a semaphore as a struct. So we can say this semaphore is a struct. Also, first I want to emphasize here we just use pseudocode to describe the structure semaphore. And in discrete operating systems such as Windows, Linux, all this, the semaphore's definition may be different, but the function or the meaning are the same, the similar as here. Okay, so as the semaphore defined as a structure with finite, first it has an integer value, represent the value of the resource it represents, and then it has a struct, it's process struct. It represents a list that waiting for this semaphore. Okay, so here assume two simple operations, block and wake up. Just now we already decided. Block places the process into a waiting queue associated with one semaphore. And wake up, a blocked process should be restarted or wake up when some other process executes a signal operation. If we have this definition and these two system operation, then we define the wait operation as the follows. Of course, this also just pseudocode. Okay, and so first we decremented the value of the semaphore by 1. Okay, then after the decrementation, if the value of the semaphore is smaller than 0, that means no resource left. So we have to add the process, actually the PCB of the process that call wait operation to the list, waiting for the semaphore. Then block the process that call the wait operation, wait operation. Okay, so block operation suspends the process that invokes it. Then as for signal operation, that means first we incremented the value of the semaphore by 1. After incrementation, if the value of the semaphore is smaller or equal to 0, that means there are already precise waiting for the semaphore. So remove a precise P from the list waiting for the semaphore. Okay. Actually, we remove what? We remove a PCB from the waiting queue to the ready queue. Then wake up the precise. Okay. So the wake up operation resumes the execution of a blocked precise P. Wait and the signal operations are provided by operating system as basic system calls. Okay. So from the definition of wait operation, we know that when the precise require resource from the operating system, he has to call the wait operation to require a resource. When it finishes using the resource and give the resource back to the system, he has called the signal operation. Okay. So know that in this implementation, semaphore values may be negative, whereas semaphore values are never negative under the classical definition of semaphores with base waiting. If a semaphore value is negative, its magnitude is the number of processes waiting on that semaphore. This fact results from switching the order of decrement and the test in the implementation of the wait operation. The list of waiting processes can be easily implemented by a link field in each process control block. Each semaphore contains an integer value and a pointer to a list of PCBs. So, wait and signal operations are atomic operations. In single processor, when wait or signal is executing, the interrupt is inhibited. It is critical that semaphore operations be executed atomically. We must guarantee that no two processes can execute wait and signal operations on the same semaphore at the same time. This is a critical section problem. Interrupts during the time the wait and signal operations are executing. This scheme works in a single processor environment because once interrupts are inhibited, instructions from different processes cannot be interleaved. Only the currently running process executes until interrupts are re-enabled and the scheduler can regain control. Okay, let's look at the semaphore usage. Okay, semaphore usage. Operating systems often distinguish between counting and binary semaphores. The value of counting semaphores can range over an unrestricted domain. Counting semaphores can be used to control access to a given resource consisting of a finite number of instances. So we can use this. You can use semaphore for mutex log. So here we have critical section. If we only have one shared data like this, we look at this example. We have learned producer, consumer problem, producer, consumer problem here. So okay, let's just produce a precise. We know that in producer problem, this statement counter plus plus is critical section. In consumer precise, this statement counter minus minus is critical section. Now we learn semaphore, so it is easy. We use one semaphore as a mutex lock. Okay, for mutex exclusion, we use one semaphore. So here, we use this mutex as a mutex lock and initialize it as 1 because we only have one shared data. Okay, and here, before enter critical section, we use wait mutex to require the resource from the system, okay, to see whether the counter can be used. Okay, and after finishing assessing it, we use signal to give back to the system. Okay, and this is so if we have semaphore, it is easy for us to implement mutex exclusion. Also, we have other usage such as this semaphore is a general synchronization tool. Okay, such as we require that execute code B in PJ only after code A executed in PI. First, we must know that PI and PJ are concurrent processes. They are equal in the write queue. Which one, or PI or PJ, will be scheduled first? We don't know because it is an active dynamic. Okay, it is not static. So we want to ensure that, to satisfy that, code A must be executed first, then code B. So we use a semaphore flag, initialize to 0, and we write PI as this. First we write A, then we use signal operation. In precise PJ, we write the code like this. First, we use wait operation, then we write B. So, no matter precise PI or PJ, which one execute first, we can satisfy, surely we can satisfy that code A will be executed first before code B. Because it suggests that, suppose that precise PJ scheduled first get CPU and execute first, but it first execute this system call because the value of flag at the beginning equal to 0. So wait operation will cause the precise PJ be blocked, suspended to the waiting queue, and release the CPU. Then when only PI execute code A and execute signal operation, then the value of flag can equal to 1. Then also give a signal to precise PJ, and precise PJ will be wake up and put into the write queue. So next time PJ execute, it will pass the wait operation and execute code B. So this is synchronization tool. Okay, so we find that if we use the semaphore as synchronization tool, the wait and signal operation for the same semaphore will be in different precise. You must remember this, will be in different precise. And if we use semaphore as mutual exclusion, for mutual exclusion, then the wait and the signal operation for the same semaphore will be in the same precise. Okay? Dialogue and starvation. The implementation of a semaphore with a waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. The event in question is the execution of a signal operation. When such a state is reached, these processes are said to be deadlocked. So let's look at an example. Consider a system consisting of two processes, P0 and P1, each accessing two semaphores, S and Q, set to value 1. So suppose that P0 executes wait S and P1 executes wait Q. When P0 executes wait Q, it must wait until P1 executes signal Q. Similarly, when P1 executes wait S, it must wait until P0 executes signal S. Since these signal operations cannot be executed, so P0 and P1 are deadlocked. Okay, so we say that a set of processes is in a deadlock state when every process in the site is waiting for an event that can be caused only by another process in the site. The events with which we are mainly concerned here are resource acquisition and release. Other types of events may result in deadlocks. Another problem related to deadlock is indefinite blocking or starvation, a situation in which processes wait indefinitely within the